Welcome to Mathematical Practice 3, the goal of which is that students would construct viable arguments and critique the reasoning of others. Like this picture of eggs and chicks, so far we've hatched some of the content that we will cover in this course. In previous lessons, we talked about changes in education and our role as change agents to prepare students for college and career. We talked about problem solving to advance rather than apply student learning. We talked about the role of the teacher in choosing challenging tasks and the characteristics of such tasks. We discussed the importance of reflection, visualization, and sense-making, brain activity, and getting smarter. This lesson on Mathematical Practice 3 is supported by current research on the value of peer-to-peer communication and on establishing a classroom culture that promotes problem solving and student communication. We will consider teacher intervention. If students are to develop significant understanding of mathematics, the question is, how much should a teacher intervene? And if a teacher intervenes, what type of intervention should take place? Why is communication important? Why do you think it's important to communicate our thinking in mathematics? In the video probe you watched to prepare for today's topic, you saw grade 2 students learning sentence frames for how to communicate with one another. In the field of education, this type of talk is called number talks or math talks. I would like you to consider this question. Why do you think it's important to communicate our thinking in mathematics? Before you click to the reasons I've listed, I encourage you to think about, even jot down reasons why you think it's important for learners to explain mathematical thinking to someone else. According to NCTM, National Council of Teachers of Mathematics, communication of mathematical thinking is important because explaining something to someone else causes us to think more deeply, to include more details than others would understand what we're saying. We stop to consider our options. What are the possible ways we could talk about this? And in thinking about talking to others, we first make a visual map for ourselves. Then, before speaking, we chart out the steps that we'll take in our explanation. And when explaining, we attempt to be in our choice of words. And we consider modifications as we go along, especially if the other person gives verbal or visual clues that suggest that they're not following our line of argument. Explaining to others causes us to view and review again and again to see if we're thinking and expressing clearly, and if we're making sense of what we're saying. We need to be able to defend our arguments in a rational way. Otherwise, all we're giving another is our opinion. When we're challenged to think and reason about mathematics and to communicate our thinking to others, we learn to be clear and convincing, which moves our argument from being an opinion to a truth statement based on supporting evidence. With this background in mind, the goal of this lesson is to help you prepare to teach so that your pre-K to grade 2 students will learn to explain math in a logical, mathematically sound manner. When children don't understand math concepts, they think there is magic in mathematics. And unfortunately, we adults often convey this same message to children. A second goal for Mathematical Practice 3 is that students will learn to give explanations of mathematical thinking that are organized, reasonable, justifiable, and laden with proof. That students will listen to teachers and peers to understand their thinking. A goal is that they would not only listen to others, but would receive feedback from others to deepen understanding and improve thinking. And the final goal for this mathematical practice is that students will learn to give feedback to others, to also deepen their understanding and their thinking. This is an example of a poster you might use in your classroom to help students understand what is expected of them according to Mathematical Practice 3. Put in the words of students. The standard says, "I can explain my thinking, and I consider the mathematical thinking of others. I can explain my strategies, and I can compare my strategies to others' strategies. I can explain my strategies using objects, drawings, actions, diagrams, words, and numbers." This goal will receive special attention in our next lesson. I listen and I ask questions to attempt to understand, to make connections between what someone else is thinking and what I'm thinking, and to think about whether what they're saying is reasonable and is supported with evidence. To better align with Mathematical Practice 3, I would add to the statements on this poster about giving and receiving feedback from others. In the upcoming slides, we will further explore each of these goals. So, the first goal again is that students would view math as logical and understandable. We would not have taught very long before we hear a student say, "I found a trick," or "My dad, sister, or grandpa showed me a trick to do this faster." Tricks are contrary to Mathematical Practice 3. Contrary, viewing math as logical, sound. There are no magic tricks in mathematics. Think about this. What is 3 times 10? What is 6 times 10? How about 8 times 10? You probably gave the answers to these questions quickly and with confidence. How did you know? Some people respond, the trick is to add a 0. First of all, this isn't a trick. A 0 is put in the ones place, while the other digit shifts to the tens place for a valid reason. The 0 isn't a trick. Rather, the 0 shows that there are no ones in the ones place. Second, you are not adding a 0. If you add a 0 to 3, you still have 3. If you add a 0 to 6, you still have 6. It's imprecise to say that you add a 0. To say so causes confusion and misconceptions, especially with young children. As we will soon learn in Mathematical Practice 6, it's important to be precise, exact with the language that we use when teaching and learning mathematics. Teaching students tricks, such as just add a 0, robs them of the chance to see connections between meaning and math. It robs students of chances to see structure and patterning. Structure and patterning is the focus of Mathematical Practices 7 and 8. To review, there are no tricks in mathematics. Yes, there are structures and there are patterns, but no magic. I would like to review the last 3 goals for Mathematical Practice 3 because these lay the foundation for the rest of this lesson, which will be on establishing a math culture. The last 3 goals for Mathematical Practice 3 are 1, to give explanations of mathematical thinking that are organized, reasonable, justifiable, and laden with proof. 2, to listen to teachers and peers to understand their thinking. 3, to receive and give feedback to deepen understanding and improve thinking. We talked about essential questions in a prior lesson. In this lesson, we will expound on the types of essential questions that are necessary to establish a math culture. Sometimes students think that if they list the steps they took, they're explaining their thinking. Not so. In a math culture, students are prompted by questions and comments to help them make their thinking visible. We might, for example, ask, "Why do you think that?" And when they respond with explanations that are underdeveloped, we might prompt them to go deeper by saying, "Tell me more." As we emphasized in an earlier lesson, make the mantra in your classroom, "Why do you think that?" Not, "What steps did you take?" not what did you get for an answer. The heart of math, as with all sciences, is to pose ideas and then either prove or disprove those ideas based on reasoned evidence, based on a chain of evidence that others can follow. Much of the work of math involves arguing to prove a hypothesis is either true or false. On the next slide, I suggest a number of why and how questions that we might ask students. Before moving to that slide, pause a moment to consider the types of questions that you might ask students to help them to focus on why rather than what. Questions to support students in giving viable explanations, to guide students and help them to understand the types of proof they are to give, to prove or disprove their conclusions. You might ask questions like the following. Why is it hard for you to explain? We could ask this when something is hard to explain, because the reason it's hard to explain is usually because we don't understand it well ourselves, or we do not yet have the vocabulary or the words to express. Another question might be, why is it easy for you to explain? Again, when we understand, we have the vocabulary, we have the understanding to express well. We might ask, why is it good to go through your explanation a few times before sharing it with others? Notice how this question and many of the other questions cause us to think more deeply, think more precisely, organize our thoughts. We might ask, why do you think this is the strongest evidence for your argument? This question makes engaging in high-level thinking what we will do, the high-level thinking that's found at two of Bloom's highest levels. When we ask, why do you think this is the strongest evidence, we are asking students to compare and contrast, and we're asking them to evaluate and rank. We might ask, how would you change your argument if you were to explain your thinking to a child younger than you? This is another high-level prompt, this time calling for justification and clarity. This question asks students to think of others, not always an easy thing for small children to do based on their highly egocentric view of the world. We might ask, how would you explain this to another child that doesn't see how your argument makes sense? Or we might ask, how do you think your argument will convince someone else? These are just a few of the many questions we can ask to direct and redirect students' thinking. Add your own essential questions to the list. Prove it. Pre-kindergarten and kindergarten can and should build the foundation for supporting our words with evidence. Build a social culture where students think and develop arguments and prove their conclusions. Only we can build that culture. And the first step starts with our own belief about the human brain. Joan Bowler wrote a book entitled The Elephant in the Classroom, Helping Children Learn and Love Math. She cautions teachers to get rid of the elephant in the room. The elephant is the belief that some students were born with a math brain. We don't say some people were born with the ability to learn history or to learn to read. Why then do we accept the myth that some children can understand math while others can't? And that only some kids are going to be good at math? Teachers and parents believe in this elephant, and they teach students to believe in the elephant when they talk about being good or not good at math, or when they say, I don't do math, or I always struggled in math, or you're just like me, I was never good at math either. Until we get rid of this myth, we will have widespread underachievement. Get rid of the elephant in the room. Believe that all of your students can be good in math. This mindset will help us to then develop our classroom community of math learners. Construct a positive social culture in your classroom by developing 4 features that distinguish a classroom community of learners: the free flowing of ideas, student autonomy, constructive use of mistakes, and the belief that logic and structure determine reasonableness and correctness. The classroom needs to be a place where there is a free flowing of ideas. To make this happen, the teacher establishes norms for how students are to interact with one another. Some of these norms are: every student will interact. Interacting is mandatory for everyone. This is not optional because, as what was discussed earlier, communicating with others is necessary for building understanding. Yes, even second language learners will interact, although in that case it's important to build scaffolds to support students who are learning the language of English and the language of math at the same time. One of the best ways to support students' learning of the language of math is with sentence starters. We will go over some of these in the following slides. Ideas flow much freer when we emphasize and believe in ourselves that every student has the potential to contribute to everyone else's learning. This means that every idea is accepted with respect and with response. Every idea is appreciated, and every idea is thoughtfully examined. A second piece of the puzzle for developing a social culture is student autonomy. We respect and we teach students to respect the need for everyone else to understand our thinking and our methods. We realize and we teach students to realize that rather than one way, there are a variety of methods that will do the job. We expect students to explore alternative methods. We ask, how else could you solve that problem? And we ask students to give a number of ways to show what this means. With student autonomy, we expect students to share their thinking with their peers. Constructive use of mistakes. As was expounded on in another lesson, mistakes must be viewed as opportunities to examine errors in reasoning and thereby raise everyone's level of analysis. MRIs show that our brains grow from making mistakes, even if we don't correct those mistakes. Our brains grow more from making mistakes than from immediately determining the answer. In my mind, this is really exciting. Don't ignore mistakes. Celebrate them and use mistakes constructively by having the student talk about mistakes and analyze them. And in the process, not only will that student's understanding grow and they're getting smarter, but those around them will as well. Logic and structure determine the reasonableness of a correct answer. This is the last puzzle piece. In a learning culture, the teacher doesn't determine the reasonableness of an answer or a method. Students don't look to the teacher to see if they're right or wrong. The reasonableness and the correctness of a solution lies in the math being studied, in the conceptual understanding of that math, not on what the teacher says. Does the logic of the argument align with the math concepts to be learned? Does the explanation and the solution make mathematical sense to the members of the community? The community determines the reasonableness and correctness of a response. For this to happen, students need to interact with one another. The last few years, jargon has developed around this understanding, around this idea of students interacting with one another. Maybe you've heard of it. It's called math talk or number talk. A quick search on Amazon comes up with a number of books with words math talk or number talk in the title, and a quick search on Google will come up with numerous hits. It's more difficult to explain and justify our thinking to others. Expect students to justify their thinking not only to us, but especially to their peers. It's easier to justify their thinking to us because we already understand the math. And if our subject matter knowledge is firm, we also understand the misconceptions that students are most likely to develop. However, when they explain their thinking to their fellow students, they need to be clear, organized, and they need to make sense. It's important for us to model and monitor students' progress. Model using essential questions and monitor students' progress. Math communication skills can be taught through teacher modeling and role-playing. Support students as their math communication grows and as they become more skilled at expressing their ideas. Monitor progress as students engage in math discussions. Draw attention to good peer-to-peer explanations and hold these up as exemplars. Encourage and promote further growth by catching each child sometime during the day to comment on their positive interaction. The next 4 slides are poster and chart ideas for question prompts and sentence frames that you might hang in your room to remind yourself and your students of the goals and expectations for Mathematical Practice 3. Such visuals will help students create a vision for expected behavior and actions. Preschool and kindergarten teachers sometimes call this turn and talk. The place to begin practicing Mathematical Practice 3 is in the preschool classroom. Math talk. Though the writing on this chart is cursive, which suggests that it's used in grade 3 or above, I include this chart here because the questions might be applied to all grades, and because the chart construction suggests that it might have been composed as a result of student input and discussion, which is another good way to get students invested in learning through number or math talks. Math talk stems. This slide gives an additional idea you might use to set up your class poster or chart. I included it because I liked how the questions and the sentence starters are categorized. On the left, the questions prompt another person to give evidence. The questions on the right are used to extend students' thinking beyond their present level. And the box on the bottom gives sentence starters for making comparisons and exercising evaluative thinking. Transfer your learning. It's now that exciting time when you transfer your learning to a real-life situation. To transfer and expand your learning, you will video record your engagement with Mathematical Practice 3. Working with a small group of children, pre-K to grade 2, you will post the video on Canvas, we'll write a reflection, and then we'll write an evidence-based reflective response to the videos of 2 other teacher peers in this class. For further directions and explicit instructions, see MAP3-2, Transfer, Construct Viable Arguments, and Critique the Reasoning of Others. Attraction is Mathematical Practice 4. You will soon find that Mathematical Practice 4 is tightly interwoven with the Mathematical Practices 1, 2, and 3 that we've already covered, and with upcoming Mathematical Practice 5. Mathematical Practice 4 will focus in on using math thinking in places other than the classroom, on simplifying harder problems, and on using pictures and objects to advance understanding. For this probe, you will watch 2 videos on modeling. You'll either watch a video on addition with kindergarten children or on modeling with subtraction in a grade 2 classroom. You will then write a reflection upon which you will notice the modeling in either of these videos. After you post your reflection, you'll read 2 peer responses and write a short 1 to 2 sentence comment. Again, take a look at MAP4-1 Probe, Model with Mathematics, for explicit instructions. I look forward to seeing you give evidence of your learning as you interact with real students.